Hi, everyone, and welcome. My name is Aya Shillal, the moderator for this session. We've reached now the fifth webinar of the event and the last for today, with the title of Introduction to Data Science and Machine Learning Applications in Geoscience, presented by Mr. Amr Moslim. Mr. Amr Moslim is a senior geophysicist with 15 years of experience. He joined the oil and gas industry in 2006. He is currently working in an international E&P oil and gas company with a broadened exposure from frontier exploration, development field, and reserves and resources quantitative estimation and certification. He started programming in early 2014 with Java, then data science with R language, and Python for machine learning and data science in geoscience. He is the inventor and owner of the Prospects Inventory, a web application for estimating stock tank, oil initially in place and gas initially in place, and portfolio management. I would like to remind you that the session is being recorded and will be shared on YouTube. And also we will share with you the attendance form in the chat box. So please make sure you fill it. So Mr. Moslim, the mic is yours, and please feel free to add anything that I didn't mention in the presentation or some informations about yourself.
Thank you very much, Aya. This is a very good presentation and introduction. Thank you very much. I will start by going directly to the talk of today, and I hope everybody will enjoy it. I have designed the presentation to cover the introduction to data science and the machine learning, and especially part of the machine learning. And we will go through all aspects of machine learning. Then we will talk about the application in geoscience. This is a very important part for most of us. All of us are geoscientists. And then I have a special slide at the end of the day. If for someone who's already want to get into this career or to know more about machine learning, he wants to join the club and learn about the machine learning and how to be a machine learning engineer. There is one slide with roadmap in order to make you comfortable how you do this yourself. The session is designed for merely 1.5 hours, and I will make a break in the middle so we can have your questions. Please feel free to ask all your questions in the chat box, and I will go through them one by one in the break and also at the end of the presentation. So I hope you enjoy it, and I hope it will give you a flavor of what is machine learning is. As I mentioned earlier, we will talk about what is the machine learning, what is different between machine learning and coding, the algorithms and the classes, the classification, the workflow, which is a very important step, how the machine learning works. This is also a very good step because people think machine learning is a kind of magic. It's not. It's based on science, and we will demonstrate this to you. And at the end of the day, we will talk about how to evaluate your model or any other model you see in, so you have the ability to judge whether this model is good enough to work with or it's not good enough. And we will go through this by some interesting applications in geoscience I have worked myself. And at the end of the day, we will talk about the roadmap to start learning machine learning. And I think this is a very good step for everyone who wants to be machine learning in the future. So without further ado, I will start directly with definition. And I think definitions are very important because it's give us all the aspects of the topic, and then we can start from. So the machine learning is a field of AI, part of the AI, artificial intelligence, that allows system to learn from past data and make intelligent decisions. This is a very important part, intelligent decisions. On their own without on their own without explicitly programmed and to improve its experience. So it's part of artificial intelligence to learn from past data to make intelligent decisions without doing hard coding and to improve its experience. And this is a very important one. We need the machine to generate decisions based on the data they already provided in the past, and then they prove their decision-making process, their decisions. It's improving and making lower error rate all with the time. And this is the part where improving its experience. And we will discuss every aspect of this during the course of the session today. One of the main things is we need to know how machine learning works and why it's different from doing just a programming or a coding. The objective of the machine learning is to teach the machine and to create models that solve the problems without hard coding, without doing conditional coding. Like if I say, if you found this condition, you have to use this equation, and if you found this other condition, you have to use another function. This is not the objective of machine learning. This is the objective of common coding or the programming languages. And this was the case in most of the softwares we are using nowadays. It's based on common coding, which means I have to do a conditional programming, functional programming, which means I have to do functions for everything. Machine learning is a different era of doing softwares and doing to get the job done. I think the next example will tell you everything. I will start with the example here from common coding. If we wanted to calculate the velocity, you have to have the data like distance and the time. And you do the function as you see it, function based on the distance and time, and you calculate basically, you divide basically the distance over the time, and then you return the velocity values. So this is a functional programming. In machine learning, it's totally different. If you see here, the data is different. The data is mass, height, and width, and the velocity itself, which means we can have input data in machine learning that is not directly related to the output we need to calculate. It's not directly related. And then we choose the machine learning model. In this case, we are choosing linear regression, because it's basic, and then we do the fitting. And here the part where the machine learning model is learning from the data. So this is learning from the past data here, and then the prediction, which means it's already learned, and we now can use it as an algorithm or a model to calculate velocity. So the main differences, as we can see here, we can have unrelated data to the same output we want to have. This is the first thing. The second thing, I don't have to have the physical equation. I will let the model figure out the relationship. So I give the model the input data, and I give the model the output data, and then the model will find the relationship for me and come back with the relationship or the physical formula as we see it here. And we will come to this in details of how the machine learning works. The tools we can use is, we have a bunch of tools in both of them. For example, in machine learning, we have Python or scikit-learn, TensorFlow. These are libraries, big libraries for doing machine learning and deep learning, and a lot of things else. In common coding, we have also Python, we have R, we have Visual Basic, Java, Go, and Excel as well. We can do this by functions in Excel, but it's not for complex tasks. Running time, most of them has the same running time, but in machine learning, most of the time is doing the data wrangling, the cleaning to mix data in proper format and so forth. In common codings, most of the time of the programmer or the developer is doing this part of the coding, which is the physical formulas to do the functions all the time. The outputs in machine learning, we have machine learning model and forecast. In common coding, we have data tables, graph, dashboards, and so on. Reproducibility, both of them can do reproducibility, and we can use them several times. What do you mean by reproducibility is we can use it more than one time without inventing the algorithm from the beginning. Domain knowledge in machine learning, it's very, very important. It's highly recommended. In common coding, it's a must. Why it's a must in common coding? Because you need to be the expert in order to know the equations, and not only the equations, but also the assumptions associated with these equations, and the conditions and circumstances for each one. In machine learning, it's not essential, it's not must, but it's better to have a very good domain knowledge. And this is very important because you need to judge the output as well. It's not only it's not about creating models, it's not about creating algorithms. It's about how useful the output is for us, and this is the main topic here. So domain knowledge is very important. What do I mean by domain knowledge also? Domain knowledge means if I'm going to use this in real estate, I have to have a domain knowledge in real estate. If I'm going to use this in rocket science, I have to have a domain knowledge of rocket science. If I need to do machine learning models in geoscience, I have to have a proper experience in geoscience as well. And this is what we mean by domain knowledge. There are two big classes in machine learning, two big categories. One of them is supervised machine learning, and the other one is unsupervised machine learning. Let's start with supervised machine learning. Let's talk about it first. As the name suggests, it's supervised, which means I have labeled data. As the example before, where we have mass, we have height, we have width, and we have velocity as well. So the velocity here is the label data, is the answer. I wanted to calculate the velocity, but firstly, I have to give the model the label data or the answer in order to find the relationship between the model, between the answer and the input data. This is the first important step at the beginning. And then after the model is already educated and learns the relationship and figure out the relationship, it will be automatic for other problems. So in supervised machine learning, the machine learning learns from an existing labeled data. Which is, in this case, we call it reference as well. We call it label data, the answer. And the model should be continuously tested. It's not only about one test, it's more than once, based on the label prediction or classification, based on the data we already provided to the model previously. On the other hand, we have unsupervised machine learning, where we have unlabeled data. we have just the inputs, and if we take the previous example of the velocity as well, so in this case we will have mass, height, and width only, without the velocity, without the label. And if the data doesn't have the label, so what should I do? Do I have a should I have a prediction? Should I have a classification? No, there is other types of process we can deal with, like clustering and dimensionality reduction, and we will come to this in details in the coming 2-3 slides. So the model in unsupervised machine learning, we can somehow use it as a conditioning or preconditioning for the supervised machine learning, and we will come to this in details. Here is the machine learning algorithms, and as we already know it, but with also the classification. So we have here the supervised machine learning, unsupervised machine learning. We have also a reinforcement learning. This is a new different branch. It's not of the scope of this session, but we can do another session for reinforcement. It's booming nowadays, but we will. It's not of the scope of this session. But the main two categories is supervised machine learning and unsupervised machine learning. And below both of them, we have a lot of machine learning algorithms. This is I have listed a few of them in the left hand side of the screen, and we will tackle one of them, which is the linear regression, and we will explain to you what is the classification, what is the regression, and what is the clustering, and what is dimensionality reduction, as an examples of these supervised and unsupervised machine learning techniques. So as we mentioned, we have supervised and unsupervised machine learning. Supervised machine learning has two subcategories, which is regression and classification. Unsupervised machine learning has two subcategories, which is dimensionality reduction and clustering. I will start with definitions for each one of them in order to understand what are those. And I'm pretty sure we are already familiar with regression and classification, and I will come to dimensionality reduction and clustering in details. So regression, I believe we all did this in high school or in college. We extensively used regression methods to use best fit. So in order to get an estimation of the relationship between two dependent parameters, so we need to have a best fit line that defines the relationship between these two variables. And there are many types of regression. I can say linear regression, logistic regression, polynomial regression, multivariant regression. We have a lot of them, and there is very important very important criteria for the regression, that the data should be numerical values. What does mean numerical values? Which means the regression cannot be done for string data or text data. We should have regression based on so in machine learning we have to do machine learning models for text data as well. So we have some workarounds in order to convert the categorical data or text data into numerical ones, and then we can use it, of course. One of the big examples and the famous example in geoscience world for regression, supervised machine learning regression models, are missing logs prediction. Most of the wells, we couldn't get the full section to be logged due to economic reasons, due to some failures of the equipment, or due to some other restrictions, environmental restrictions, for example. So most of the time we end up with some of missing logs in our data set. So one of the biggest example and the most famous example nowadays is predicting missing logs using machine learning models. And I will show you a very good example at the end of the session. Next, we have classification. And what is the classification? Classification is another word for categorization. And as the picture here suggests that we wanted to draw a line between two different variables, two different categories. Like this could be shale, this could be sand. So I have to define what is the sand and what's the shale based on a line, or based on a criteria to define these two different classes. In classification, we have to have a predefined classes, and we then wanted to put each point of the data or each row of the data we have into one of those classes. I could have also multiple classes, more than once, of course. So more than two classes, I mean, and feel free. We have in the facies log, for example, we have sand, shale, limestone, marl, a lot of classes or facies. And that's why it's one of the biggest or the most common ways to predict facies classification is by using machine learning. And machine learning is doing a very good job actually in facies classification and prediction. This is really, really well-rounded, and you can find a lot of papers nowadays illustrating how they do facies classification based on the machine learning algorithms. And this is also a supervised machine learning algorithm. So I have to give a facies log in the beginning, and then the model will learn from the facies log, and then will come back to me with a model that already learned the relationship between the well logs and the facies log, and then we start to use this one for unknown wells, so we can generate a lot of wells. The very beginning, or the very first application for classification was in fraud detection, and this is how our inboxes decide which emails are spams or which are not, and this is based on the classification algorithm as well. On the other hand, we have the unsupervised machine learning, and we discussed before we have two subcategories, which is dimensionality reduction and the clustering. I will start with clustering since it's very close to the meaning of classification, but it's totally different. As we agreed, unsupervised machine learning, we don't have data, so we don't have the facies log. So in this case, we will need to subclass or cluster the data, or do a categorization for the data points based on their criteria, based on their data definitions, not based on a predefined classes. So the difference between classification and the clustering: in classifications, I have predefined the classes. I know them previously before doing the model. In clustering, I don't know the classes. I don't have classes. I wanted to separate the data, partitioning data based on their own characteristics, not based on a predefined class. And as mentioned here, we don't have predefined classes. Similar data points properties clusters together, and this is one of the biggest techniques we use in facies classification, but for the first time. So if I have a green field on or a few data points, I didn't create the fish log first, so I can use the well logs coming from this well and do a fishes classification. In this case, will be named as fishes clustering to be specific. To do clustering first, and then I can define myself where is the sand, where is the shale, where is the limestone, and etc. And then I can use this facies log I generated already by clustering in order to use it in the facies classification in supervised machine learning. And that's how that's why we said that unsupervised machine learning can be used as pre-data conditioning for supervised machine learning. I can start by doing facies classification first, and then afterwards I can use this facies clustering in facies classification problem for other wells. So this is one of the applications of the integration of machine learning between supervised and unsupervised machine learning. Next, we will talk about dimensionality reduction, but let's first, I want to talk to you about the dimensions. What do we mean by dimensionality reduction? In geoscience world, we have a lot of data with different dimensions. Like in the well logs, the gamma ray log, for example, it's all about 1D dimension. Maps, we have 2D representation. In seismic cubes, for example, we have 3D representation. And the more we have data, the more we can get in a better decision. But actually, Richard Bellman has different point of view. One of the biggest, one of the famous statisticians. He already developed the concept of the curse of dimensionality, and this means the more you have dimensions in the data, the more you have data redundancy, and the more it costs you computation time. And this is totally true. And we can see it in a lot of data. The more data you have, the more you get confused by different data points and take more time in calculations and processing. So dimensions, or have more dimensions of data, has its own limitations. First, one of the biggest limitation we already mentioned is the computation time. This will take a lot of computation time, expensive time. The second is the redundancy of the data. So we may have data that are redundant, like if you are doing a machine learning algorithm for real estate, for example, and you have apartments, you already enlisted the length and width and the area. So the area including already the length and width. So you already have a redundancy by having these three features together. It's better to have one of them, and it's the area, of course, and delete the two others in order to make the data less redundant. And the last thing we have in higher dimension data is its limitation. It's our own limitation actually to visualize more than 3D. So we human are very good in visualizing data in 3D, 1, 2, 3Ds, but more than this, it's not gonna work for us. So we always try to find ways to visualize data in this amount of 3D data visualization we have. So I will come back to the previous slide now and talk about dimensionality reduction. There is a certain techniques. That's why I'm stressing on dimensionality reduction, because we didn't have this concept in education at my time, at least. We didn't consider having these techniques, but there is some techniques and the statistical methods that already implemented and already there, that we can reduce the data volume and data dimensionality without losing the information. and this is the tricky part. This is the most interesting part as well. We can minimize the data without losing information. So we can then visualize the data better. We can do a processing to the data in a good time without any expensive time of computation. And we can also remove the collinearity or redundancy in the data. So dimensionality reduction, one of the biggest concept, one of the I cannot stress enough, but I use it in all the data we have, because we usually deal with big data, and the big data now is very big. So we have to have a techniques that minimizes this data without losing the information. And this is the most important part, without losing the information. Here I will have some questions and answer before we continue to the processing workflow. Okay. Is it safe to say that supervised learning label data is similar to the process used in calibration of any equipment, meaning to calibrate the accuracy of any equipment, you would use standard reference tool or another standard reference equipment? Let's call it label data to calibrate said equipment to its closest accuracy. I can say yes, I can say this, and we do calibration all the time. It's testing, it's not calibration. Calibration, you want to have the same result exactly, but in machine learning, we wanted to make sure that we are directionally right rather than precisely wrong. And this is a very important concept. We want to make sure that we already directionally right. We are heading to the right direction because we are looking for patterns. We are not looking for a very precise values. This is one of the important concepts. Thank you. Dimensionality by principal component analysis. Exactly, this is one of the methods, principal component analysis. And there's another technique called support singular value decomposition, and a lot of techniques actually for dimensionality reduction. But the main concept of all of them is to try to minimize the volume of the data without losing the information. This is very important. I need to be mentor in this area of application of machine learning to reservoir characterization and reservoir modeling. This is a very good objective, and I can help you. Certainly after this session, you will have the full foundation and the basic concepts of machine learning, and you can start from there. Okay, if you have any more questions, please put it in the chat box, and I will come back to this one by one. Okay, so in the coming slides, we are going to talk about the machine learning workflow, and we'll start from there. The machine learning workflow, it's very simple and essential as well. So let's talk about it. In the beginning, what we need is to have this data, and then we import this data first. Then we do data exploration. World, we have different data. We have GIS data, we have LAS files, we have DLIS files, we have SIGY data, and the SIGY data is binary in binary format, and it's not easy to work with. But we already have done this, and there's already ready-made libraries now that can already read and write and manipulate this binary and ASCII formats for us. The second step is data exploration, which is the very, very important ones. However, يعني you think you know your data, you need to do data exploration. And I believe in my course that we already do this before, even know that we already do the machine learning workflow. The first thing, we get the data from the field or from data vendor. What we do is actually we import data to softwares and we do some exploration. We see the data, we try to figure out what does this data means, part of the QC. But in this particular one, we are not only QC the data, but we are trying to figure out if there is any relationship between the data. We need to know the data limits. We need to know the data distributions, how we can improve the data, and we need to understand fully the data inside out. After we already understand the data, we go to the next step, which is data cleaning and filtering and fixing, because as I mentioned before, most of the data we get it from the field or from any data vendor. We need to rearrange data in order to make it visible and easy to us to work with. So we need to cleanse data, we need to do some filters, we need to focus only on the data we need and try to remove most of the data that we don't want, or we will make our life harder. So, and again, we need to do some cleaning or fixing for this data. Then we do a feature engineering and selection. And this is actually a unique for machine learning and data science step or workflow. Feature engineering, because we want, at the end of the day, we want to put the data in the format that already matches with the algorithm. And can the algorithm understand the data format easily, so it can work on this one. Some of the algorithms has a problem with missing values, for example. Some of the algorithms performing better if the data all distributed normally. Some of the data, they don't care about if they have text or strings, and some models cannot work with numerical and categorical data at the same time. So we need to do some feature engineering to change the nature of the data we have in order to make it easier and efficient to the algorithm to run with. So we have a lot of data conditioning in the beginning. We do normalization, we do standardization, we do one-hot encoding, which is converting the text into numerical by doing one-hot encoding. We do also handling the missing values to choose which value we should add to some missing values, or we should remove them all if they are a limited amount of missing values. So we do a lot of feature engineering, and this is called feature engineering because every column in the data we call it feature, and every row we call it observation. So for each column we have features, and for each row we call it observation. So afterwards we do train test split. After doing our feature engineering, we do train test split, and this is a very important part of the machine learning, because in this part we don't want to run the algorithm on all the data directly. We want to split the data into training data, which is the one that the machine learning will learn from, the model will learn from, and to test at the end of the training, we need to test is the model already learned efficiently or not. So we need to test the learning of the machine or the model, and come back to improve this one. And here where it comes the model evaluation and the improvement. So I need to train the data and then test the training, and if it is okay, so okay. If it's not, I need to improve it all the time in order to make better decisions and a better understanding of the relationship between the data itself. And after the training test split and before the model evaluation, we have a model selection, because as we said before, we saw it before, we have a lot of machine learning algorithms, and model we can use in all the categories. So we need to select best one. Usually we don't use one directly and work with it. We use like 4, 5, 6 different models and try it first with everything. So we build a base model, we call it base model, and then we choose from them which one we are going to enhance over time. So this is basically the machine learning workflow, starting from importing data, exploring the data points, what is the limits, what is the relationship between the features together, and then we do some cleaning and filtering, and then we change the data to meet the model by feature engineering, and then we do train test split to split the data between a training and testing, so we can test the model efficiency, and then select the model and do model evaluation at the end of the day. 80% of our time is here, from data exploration to test split data and model evaluation. Running the model is very, very easy and very simple for us. It's not a big deal now. We have already ready-made libraries that do this for us. So it's not a problem at all for us to select and run the model. Even we have some libraries that run a lot of models and select the best one for us. But what is really a talent and an art for machine learning is the model evaluation and the feature engineering, because both of them are the ones that will already make a huge difference impacting the accuracy of your model. So here I'm going to talk one more time about the training test split, because normally what we do is we train, we split the data into training and testing. But there is one more step we wanted to discuss with you, is validation. So we split the data between training, testing, and validation data. Normally, the training part is the biggest part, which is from 60 to 80% of the data. And the testing data is from 40 to 20% of the data. The more data you have, the more training will be, and the less testing and validation will be. The objective of this slide that we don't usually consider one training segment of the data. We consider a shuffling of the data all the time, so we can have all the observation in the training and testing as well. So we shuffle the training data and testing data, so the algorithm can see all the data in the training and see all the testing in the testing process as well. And the reason for that is because we already have some of the data have some imbalances, trends. Like if we have a sand shale sequence in one of the wells, and we have a very thin layer of limestone, this layer will be not represented enough as the sand and shale sequence. So this is what we call it imbalance classes, and we need the algorithm to see enough of the data for limestone in order to understand the relationship, to know the relationship between sand, shale, and limestone, and the differences between them. So we need the algorithm to see all the data points all the time. But also we need to get some validation data outside of our method, totally aside. So in order to make a proper judgment on the algorithm using a validation data set as well. So the testing data set is to make the model improve its experience and learn more. The validation data set is to get the final scoring of the data, the final accuracy of the model. Through the validation data set. So it's basically you can do with training and testing only, but also you can, or it's better to separate the data, split the data into training, testing, and validation as well. Okay. I think I will have questions. I will answer some questions, if any, and then I come back to the presentation. I'm not quite sure of this one. Okay. If you have any other questions, please submit your question in the chat box, and I will return back to it. The reason for this, I want to give you some break before model evaluation. We want to talk here about how we evaluate our machine learning models. We cannot run a machine learning model on the old data we have, because by this we don't know how the model performing. Is it performing good or bad? We don't know. We wanted to make the model as accurate as it can be, and I can use it generally in all problems afterwards, or similar problems, if I can see so. If in the beginning I wanted to tell you something, if the machine learning model or the machine learning model is a human being, it will have two legs. One of them is generalization, and the other is optimization. So we will learn about both of them in the coming slide, in the coming section. The evaluation, the generalization and optimization. Generalization is we want the model to be directionally right, to understand the trend inside the data. We don't want to have and save the data values in the memory. No, we want the model to understand what trends, what patterns inside this data, and this is the most important. And this is what we call it generalization. The other concept is the optimization, and we will talk about in a bit in how machine learning works. But here we need to make sure that our model is generalized, not specified to each value or specific to each value. Okay. In order to test the model, we have to have an error function. I have to define the error. What is the percentage of the error in order to make this error less all the time? So what we call it loss function and cost function, and sometimes you will hear error function. So all these are the same, almost the same thing: loss function, cost function, and error function as well. So we basically, in regression models, we have mean square error, root mean square error, and of course R squared. And I know all of us has been already introduced to these methods during high school or college, when we solving already regression problems or best fit problems. Okay, after we already define our loss function, our cost function, we expect that when we have more time training our model, this is a training score, we have more time training our model, the error rate will drop until it reach a point where any more training for the model will not yield to another dropping in the error rate. So the error rate is stabilized. Maybe it could be 1%, 2%, 5%, or 0% sometimes. It's no problem at all. But we expect that the more complex the model we have, complexity here goes both ways, either to run the model more or to do a complex hyperparameter, to do more parameterization, to add more value inside the model. So the more we train the model, the more the error will drop until we reach to a satisfied range of error rate, and this we will stop here training. But on the other hand, when we test the model, we see a very distinguished criteria. After certain threshold of error, the testing error become increasing. We expect to have the same behavior for the testing, so the error drop for training, and the error should drop also for the testing data, because training data and testing data are the same data anyway. So we should have both of them dropping all the time. However, this is not the case. At some certain point, the testing error start building up again and have more error while we are training the data. And the reason for this is we already overfitting our model, overfitting our data, and we'll come to this later. But let's start here. Why we have high error rate in the training and the high error rate in the testing. I will come to this after a while. But if we have high error rate in the training and the high error rate in the testing, that means I have underfitting model. Underfitting model means the model, as you can see here, it's by model. We can fit it with a different line, but the model here assumed it's already a linear model. And this is the underfitting part. It's the model is not fitting the data, so it's underfitting the data. On the other hand, we have lower training score, error score, and we have higher testing error score, which means the model is overfitting the data, which means he treated every point as a separate model. The model is treating every point as a separate model. So he built a linear relationship between both of them here, and another linear relationship here, another linear relationship here, and it goes all the way time by this squiggle line. So this, as we can see, it's not the model we already, the general model we are expecting from our machine learning model, but it's already fitting every single point. And this is why I said we need to make sure that we are directionally right, not precisely wrong. Here in this point, we are precisely wrong. For every point, we get a very low training rate, but if I add another point, it will change, it will give me a huge error in the testing, and this is what happened already in the testing here. So when the model saves and keeps the data in the memory, and already finding a model for every data point, separate model for every data point, it already increases the error rate in the testing data. What we really need for machine learning, our machine learning model, is to find the generalized model that describes data, because all data we have including noise. There is no free noise data. Most of the data we are working with, if it is real data, it will have noise. And this noise that keeps the model fluctuating from positive and negative side. So you want the model to understand the trend, not the noise. So he can suppress the noise and just generalize around the data points. And here, where is the sweet spot we have here? And this is the most generalized model. And this is the best model and best parameter we can get for this model. This is the model evaluation, how do we evaluate our training. This is how we evaluate our machine learning model. So basically, we draw the training score and we draw as well the testing score. And when we see the testing score is building up here and exactly here in this point, where we know that we need to have our model to be stop complexity at this point. So we need to stop iteration, we need to stop training, we need to stop our hyperparameter as well. So basically, when we have the lowest value for error, testing error, and also a low error rate or acceptable error rate for the training, here we can have the most generalized part of model evaluation and the best model or the optimal model, as we can say. This is the model evaluation for regression. What we have described is the model evaluation for regression. For classification problems, the problems like I wanted to classify the sand from the shale, the sand from the shale from the lime. These problems, we have different techniques. The different technique here for classification is the confusion matrix. The confusion matrix is a table between the true classes and predicted classes. So this is how it should be. And this is the prediction comes from the machine learning model. And let me give you an example for what we have now in this pandemic. If you God forbid you tested for coronavirus and you get your test is positive, you need to look at this confusion matrix. If you get your test is positive and you feel yourself sick, so you are really true positive. You are sick, this is true, and your test is positive. So the prediction matches the actual, and this is a true positive. And if you got if you tested for coronavirus and you get negative, and you know you are a healthy person, so it's negative testing, and this is true as well because you are healthy. So it is true negative. So in these two cases, the test is correct. Either you are already a sick person tested positive, or a healthy person tested negative. So in both cases are correct. The other two errors are if you already a healthy person and you tested positive, this is an error, of course. And the other error, if you already a positive or a sick person and the test comes negative, so this is a false negative. So this is what we call the confusion matrix. And from the confusion matrix, from these four numbers, we get a bunch of calculations based on these four squares. And it's needless to say, this four squares only for one class or two classes in this case. But if we have more classes, we will have more boxes, but all with the same concept: true positive, false positive, true negative, false negative. These are the basics ones. And this is how we do model evaluation in four classification problems. Okay. Here we are going to talk about how this machine learning works, what is the magic behind it, And I think after this one, you will not find any magic. You will find it's based on mathematics and based on statistics, and it's not a very complicated issue as well. It's not very complicated mathematics. It's very simple mathematics. So I will start by explaining to you the linear regression, and I choose linear regression because, as I mentioned before, we already have done this several times in high school or in college. Basically, everything we do in any lab just to draw two variables and to find the best fit between them. So basically, we know what is a linear regression there. And linear regression is basically follows this equation where y variable equal x plus b, which is a is the slope of the line, and you can call it gradient as well. And b is the intercept or the anchoring point of the line. So we need to find a and b, and in this case we will look for a as just a simple example. And let me remind you how we did this in previous, before machine learning era. We basically start with a random number to find a, for example, the slope. We start with a random number, let's say 1, and I will try to calculate this equation and find the predicted y. And I will take y actual minus y prediction, and I calculate the error. And then I will change a from 1 to 2. And I do the same, calculate the equation, and then calculate the predicted y, and calculate the error between y actual and y predicted, and see the error. If the error is going down, so I'm heading to the right track. If the error is going up, I will change the values from 2 to 0.5, for example, to the other direction. And at the end of the day, we will have an error function like this. We start with 1, with 2, and the error keeps going down, until we find the optimum value here for A. And then I know its optimum value because after we already do some other trials with fixed increment, I see the error value is starting build up again. So at the bottom here, or at the trough of this error function, the one in red, as the trough of this one, this is the optimum value for A. And this is how we do it. So we use random value and fixed increment all the time. In machine learning, we wanted to do all of this, but we wanted to do it automatically without our interfering, without doing a fixed increment as well. So basically, if we think about it, this is the error function, the one in red. And to find here the optimum value directly, I need to get the tangent for this curve. The tangent for this curve will give me the slope. And if the slope equal to 0, it means it is in the bottom here. So the tangent or the slope of this curve can be changing all the time until I find the slope equals 0, which means the slope is horizontal line, exactly like this. If the slope is horizontal line, so I find already the optimum value. So mathematically, how we can do this? The slope is, we can get it very easy by first derivative. So basically, I should calculate the first derivative at each point here. And when the first derivative equal to 0, this means that I have here the optimum value, the best value for predicting the slope. Okay, this is a good start. So basically, I have to find the slope of the cost function or the residual function and make it equal to 0. And if I find the value where the first derivative equal to 0, so I have here the value of A. So this is basically easy. The second step is the increment. I use already increment in our previous experiment when we do in college or in high school. We do fixed increment, like move every one, and that's it. But what if one is very huge? What if the values I wanted is 0.0001? This is the value, is the optimum here. So I will take a lot of time in order to reach this value. And sometimes I maybe miss the value. If I jumped from 1 to 2 to 3 to 4, and the value is very small, I cannot get into the optimum value here. In this case, we will, in machine learning case, we will use what we call it learning rate. Learning rate is the rate that we will change these points every time of calculation. What if I have a big error here? I think it's not a problem at all. But what if I take a small percentage of this error every time? I'm not talking a fixed increment, fixed number, it's percentage. So if I have here a big error, I will take 10% of this error, and the next move, I will move a big jump right here. The more I come to the optimum value, or the correct value, the error will be lower. And the more I will take a percentage from the error. I'm not taking a fixed increment. So to start from here to there, or start from here to there will be have a big jump, and then a little jump, and then more little one, and another little one, until I find to the optimum value of predicting the slope. So by this means, but by these two concepts, I'm going to do it automatically. The first one is to find the slope or the first derivative of the error function to find the lowest value here, and then I will be moving by using the learning rate, not by fixed increment. In the coming slide, I have this already GIF file that explains exactly what I have shown to you now. And it's doing it already automatically. So you can see every concept we have seen in this, but in action as well. As you can see here, the start was big random value, and then the next value is big jump, and then another value here is less than the first one, and another jump here is less and less and less and less until we find the optimum value. Where is the optimum value? When the slope of the error curve equals to 0. And you can see here the data point and how this line is fitting the data point one by one. And finally, it reaches to the optimum value of fitting. This method called gradient descent, gradient because it's going by learning rate gradually in gradient, and descent because we are descending from higher error rate into lower error rate all the time. So this is basically how machine learning works. It's based on mathematics. It's based on in some other methods based on statistics, but it's not any complex ones as most of the people are anticipating. It's basic. I believe most of us already know what is the first derivative is, and we already studied calculus in college more than once. So it's all basic stuff, but when we put them together with simple concepts, we can get into very fancy results like in machine learning. We have some characteristics for gradient descent we need to understand. The first one is gradient descent is based on calculus, and as you said, as you saw, we already have first derivative in order to calculate the gradient descent. Then the gradient descent is different from algorithm to another. It's what we have seen in this example is just 2 parameters, so it's very basic and very easy to understand gradient descent. But look here in this figure, we have, this is one of neural network gradient descent functions. As you can see, it's very complicated function to have higher error here and low error here. And gradient descent also can has local minima. This is what we call it local minimum or local minima, and this is local minima, and this is the global one. This is what we want our algorithm to go to, and to have the lowest error possible. But also gradient descent can be trapped in one of this local minimum, and there is some techniques in order to make it go from local minima into global minimum as well. Learning rate is essential step to reach healthy gradient descent, as we call it. And learning rate also can be cause of overfitting and underfitting. If we didn't choose learning rate carefully, we can end up in the same situation like increment. So we can do overfitting or underfitting based on the learning rate as well. So the hyperparameter or the parameters of machine learning, including as well the learning rate and the gradient descent. Once more, one of the biggest or one of the most famous optimizer that we already use in machine learning. And here I need to repeat again, if the machine learning is a human being and has 2 legs, one of them will be generalization and the other will be optimization. And the gradient descent is one of the optimizers that we already extensively use in most of the machine learning models, as well as in deep learning in some cases as well, with some modifications. It's the basic and more efficient until we have already other optimizers that work better for complex problems. And finally, we reach to the final stage in our sessions, the applications in oil and gas industry. And before this, I want to take, if there's any questions, I would love to answer, and then we can come back to the applications. From Muhammad, in my research work, I'm working to predict and extract fault from seismic data. This is very good. I have 3D seismic cube and also created 3D label cube of the same size. Now, for training, I'm looking to create 28 by 128. Okay, small cubes for big 3D seismic fault labels. Can you please let me what is the best way, or Python library can help me? Yes, of course. There is a Python library already used convolutional neural network. I can post it already on my GitHub, or I can post about it on the LinkedIn, and I have already tested this one in different basins, and it gives a very good results actually. But it's using convolutional neural network, which is a deep learning. It's more advanced than the machine learning, but it's there, and we are working with right now actually. Yes, I can do this, of course. Please send attendance. Please, gentlemen and ladies, send the attendance to the organizers. For any model, what is the acceptable value for model or fit R square? R square is very easy because it's from 0 to 100, and we always want to have 100 or 1. So the more higher you get the R squared, the better the model, of course. But it depends on the problem as well. For problems R is very complicated, as emotions have accuracy of 58%, is something extraordinary. For velocity prediction, have 90% accuracy is not a good thing. So it based on the problem as well. So some problems are very complicated. So you have to have a base model first. This is my advice. Interesting lecture. Thank you, Hadi. I believe the organizers will post already the recording on their YouTube channel, and I think I will share it already on my LinkedIn as well. Is it a must to learn R and Python programming language? You can start with one of them. This is better. To be a full stack or to be a better data scientist, you have to have both. Python are extremely propagating nowadays. Extremely demanding. Most of all the companies actually wants Python, so I recommend to start with Python programming, and then you can flourish your experiment or skill set by doing R and SQL as well. I'm coming to this as well in the last slide, the roadmap. I'm also working on CNN. This is very good, Muhammad. I think this is the way you do it, because it's seismic is very complex, and the problems around seismic is very, very complex. That's why we need complex solutions for complex problems. Thank you. You're welcome. You're welcome. What about attendance? Please, gentlemen and ladies, do the attendance. How can I deviate to data science and machine learning? I'm coming to that in the last slide. In the last slide, I have a roadmap where I will tell you how what a skill set you should acquire in order to consider yourself on a data scientist, or on the track to acquire data science and machine learning skill set. Okay, let's continue with our lecture, and at the end I will open the chat box again. So if you have any questions, please post it in the chat box, and of course I will answer it as soon as I finish. Okay, the flavor part. My favorite part is to see how this actually, if this actually worked, and if this already we can use it in our day-to-day tasks. And actually, this is my motive when I start learning machine learning applications. I start working with a company that we have fields all over the world, and actually I am responsible for I think 6 fields now. So be able to automate things will make my life easier. And this is how I actually describe machine learning applications. Machine learning, if you did it right, it will make your life easier all the time. Let's start. Here is the most pronounced example for machine learning application, the fishes classification using well logs. We will show you this in a bit. Velocity prediction using seismic attributes. Also, I will show you in the coming slides. Permeability prediction using petrophysical volumes, fishes classification using seismic attributes, and seismic inversion using multi-solver problems or algorithms, where some basins and some geological settings where seismic inversion is not really a good solution, or not giving a very robust solution. So we already go to machine learning in order to be able to do seismic inversion based on machine learning algorithms, where the classic inversion cannot work. Okay, I will start with very good example, and in order to understand it, we are using the seismic data attributes to predict the porosity log. We have here amplitude, first derivative. This is seismic attributes. The amplitude, first derivative, second derivative, envelope, variance, wave number, because this seismic in depth, and we have phase or instantaneous phase. And the red curve here is the predicted porosity after we already linked the seismic into the porosity, into the well data. And in the other one here, the last one, we have two tracks, one in red and one in blue. The red one is the predicted porosity, and the blue one are the actual porosity. So as you can see here, the red or the predicted porosity is overlapping actually the actual porosity. So as you can see, the algorithm did a very good job actually in predicting the porosity all over the well. And because this is already an effective porosity, you can see some values are already diminishing. This is the values where we have shell streaks, and we have here the values where we already have porosity values from the sand bodies. Let's see it in another example, which is after we already finish the training and already have the seismic attributes linked to the porosity, and the predicted porosity comes very good with higher accuracy with the actual porosity. We converted it into a predicted size porosity cube using the seismic attributes, using the trained already well data. So as you can see here, this is the porosity cube in the background, and we have here one of the test wells. And as you can see, we have here high porosity values correlated with already the red and the green reflectors, and we have low values here correlated with the white reflector, and same here. It's very well correlated, as you can see. Even in this part, we have already a good prediction on this one, and in this one as well. And as you can see here, very limited values for the porosity, and we have here another good values for the porosity correlated with this reflector. And this is basically exactly the seismic inversion, seismic based inversion, machine learning based inversion I was talking to you about in the previous slide. So we start from the well data and seismic attributes on 1D level, and then we propagate this one into 3D predicted porosity cube based on the machine learning, give us a very good continuity and a very good prediction for the porosity value. And this project, I have done it myself, and it came up with very good results so far. The next application as well is doing facies classification using well log. This data comes from a competition called Force 2020 in year 2020, and they give us around 90 wells or 93 wells, and this is the facies log. This is already the facies already provided as a label data here, and this is the log data, and I just display one of them, and we can can do prediction with different algorithms. Here we use supportive vector classifier. Here we use logistic regression, and in this track we are using random forest classification. And you can see in mostly we have a good correlation and good classification for most of them, even for slight streaks like these ones here. And you see the random forest is doing a very good job actually seeing this imbalanced data, low representation in the data. As you can see, this is two different streaks from the whole log, so it can predict it very nicely. So we can do a lot of prediction as a lot of algorithms, as you see, and then you can choose which one you can use for the whole data thing. After you already did this prediction, you can propagate all your prediction into the 90 wells. So instead of doing facies classification manually, I think one well, if you are a fast geologist, will take you I think half a day. So for 90 wells, it will take 45 working days. This could be easily around 4 to 5 months. And just to do facies classification using machine learning will save you at least 4 to 5 months. This whole work have been done in matter of a day something, and you can propagate to 90 well in no time, of course. The last one I want to share with you is a project I have been working with for almost 3 months, is to try to enhance the seismic data resolution. And as you can see here, this is the frequency spectrum for a low seismic data cube. As you can see, low frequency, very pronounced, and the dominant frequency here is about 17 hertz, 17 to 18 hertz. So we have a low velocity, low resolution cube. And we use a different technique called transfer learning. It's an advanced technique, but in this technique, you teach a model using deep learning model, and then you transfer the knowledge from this data to another data. So here you can see this is the old dominant frequency for the low resolution cube, and now we have here the new frequency for the new machine learning enhanced seismic resolution. And as you can see, we can basically double the resolution from 17 to 18 almost to 33 or 34. So this is really an ambitious project, and I'm hoping to continue working on this one, because it's already enhancing the seismic resolution with a very cost-effective way, without shooting another seismic data or doing a reprocessing for the seismic data. And here, the same project, as I show you, this is already the purple one, is the seismic data, seismic filter data, low resolution, and this is the original seismic data. And in between here, this whole new data is already the enhanced seismic resolution using machine learning. So we could add more frequencies based on seismic transfer learning, using the existing seismic data we have with the new technique we already done in machine learning and transfer learning approach. This is the applications I have, and from there we have here the last slide. The last slide about the roadmap, how we already do. If I wanted to be a machine learning engineer, how to enhance my skill set, or how to build my skill set in order to be a good machine learning engineer, and use these techniques in my day-to-day activities. I see it in 4 phases. The first phase is to start learning a programming language like Python, R, and SQL. And in this language, I'm highlighting here the basic libraries you need to know. So if you want to start, you can go to Python and search by the library name, and you can find a lot of tutorial about these libraries and how to use these libraries in Python or R. The next phase is to learn data wrangling techniques and databases. This is very important because, as we said before, 80% of our time is going to data wrangling and making data in better shape in order to make the algorithm run efficiently and smoothly. So in this phase, what you will learn is these libraries from Python. SciPy, it's a scientific Python library. OpsPy, it's another scientific Python library as well. You can use this OpsPy in order to load seismic data, as I have done in I think 2 years, but I will show you something better. A stat model is to do statistical model broadly for plotting. In R, you can use tidyverse and tidy models, ggplot for plotting. These are the libraries are really wanted to build your skills on. Third phase is you need to learn mathematics, statistics, linear algebra, and calculus, and don't be overwhelmed with these terms. We need to learn just the basic stuff. The probabilities, center measures, variation. This is all basic stuff, and don't rush yourself into learning mathematics first. Just start by learning the languages, programming languages first, and learn mathematics as you go by learning machine learning. So for every algorithm, you will know how this algorithm works, and then you can search for the mathematical formula and understand the mathematical concept afterwards. So don't get overwhelmed with this mathematical thing. It's all the basic stuff, nothing fancy at the beginning at all. The final step is to go and learn the machine learning algorithm itself. So for each machine learning, you need to know the basic idea, how this works, exactly how, as like we already demonstrate and illustrate linear regression. You need to know the essence of each machine learning technique. And in this presentation, I have enlisted the most famous machine learning techniques. If you learn them, you can consider yourself in intermediate level or past the intermediate level, because those are the machine learning algorithms that will give you a very strong background and foundation for everything else. And most of the problems can be solved with this machine learning algorithm I have mentioned already earlier in the presentation. The machine learning packages, you need to learn TensorFlow for neural networks and deep learning, and as we mentioned already, CNN, and there is another library called the PyTorch. If you want to TensorFlow or PyTorch, it's up to you. Both of them are okay. Keras for machine learning algorithm, scikit-learn for machine learning algorithm, and the model evaluation as well. And to get everything together, and for geoscience especially, there is already Python packages that will help you to flourish your experience and skill set with a lot of seismic, with a lot of Python experience. We have Willy and LAS.io. These two libraries are for reading and writing well logs and LAS files, so you can handle the LAS files. SIGY.io for handling SIGY files. It's very difficult. That's why it's you need to have a library dedicated only for SIGY input and output, or manipulation and handling. And BitRuby, it's a petrophysical evaluation library. You can use it instead of use any expensive softwares to do your petrophysical evaluation. And there is another library called the GIIP if you wanted to do static model and dynamic model for using Python without using any softwares. Up to here, I finished my presentation. Thank you very much for listening, and I hope I give you some flavor of the machine learning and give you a strong background that you can start from it to build your skill set in the machine learning. I'm going to answer the rest of questions, and if you have any other question, feel free to ask me. Based on your experience, what is the suggested in classic environment? It's worth to generate inversion cube using machine learning to map thin sand bodies. Yes, it's of course worth trying, but you are also wanted to test it against the seismic resolution, because if we wanted to do this, we need to understand the seismic resolution. I'm not saying it's not gonna happen, it will happen. And the seismic inversion is machine learning. Seismic inversion is the best alternative when the classic inversion is not working due to seismic resolution and due to any other problems in the data. A great example of porosity prediction. What machine learning method is used for this one? It's random forest. I used random forest, and I used also XGBoost. And I need to be fair, I used 5 or 6 methods in order to choose from them. And the best one in prediction porosity from seismic was random forest, and the second one was XGBoost. Can you explain more what is the ML you use for the prediction of? Yes, this is as I mentioned, random forest and XGBoost. Both of them give me a very good results. Thank you for showing us the great example of sound resolution. Thank you very much. Can you please let me know how you manage to suppress the noise during the process? Actually, I'm not suppressing the noise. To be fair, there is some noise already generated in the process while I'm doing the process, but this is all random noise. I totally overcome this with a simple median filter, without any additional filtering. So it was easy for this example. And now I have the transfer learning ready-made, the algorithm I mean, or the model ready-made. I can use it for any other seismic data in the future. Which material can you recommend, and can you be my mentor? Of course, it's my pleasure to be your mentor. And I have a lot of material in my GitHub. If it's okay, I can share it with you here or on LinkedIn as you like, and we can start our connection from there. I have a lot of materials in my GitHub repo, and I can you will find a lot of interesting material in there. I hope so. Thank you very much. It's my pleasure. Hello, did you send attendee sheet? Please send the attendee sheet. Thank you very much. after having a machine learning model, how can we explain a good correlation between two parameters without a logical explanation? Can you elaborate on this one, please? It's a very important topic. Please elaborate on this one. How can we explain a good correlation between two parameters without logical explanation? Okay, first I would like to remind you and myself as well that correlation doesn't imply causation. This is very important one. So having two parameters correlated to each other doesn't mean they have a common logical explanation between both of them. There is an explanation, but there is no causation between both of them. And this is as far as I understand it from your questions. You're welcome. You're welcome. Today is one of the happiest day of my life. Thank you very much. Don't be scared. It's easy. Thank you very much. Please, can you explain more about the prediction process of seismic cube attribute using machine learning, how it works? It works by first you have seismic data, seismic cube, and then you have to generate some attributes. This attributes is very important, and the choosing of attributes is very important as well, because not all the attribute will help you in prediction of porosity, and also you can have some attributes that can make some redundancy with the seismic data or with other attributes. There is the first thing. The second thing, you need to carefully link the seismic data and seismic attributes to the well data. This is the most important or second important thing, is to seismic to well tie. In my case, it wasn't any problem because I have already seismic in depth, but if you have seismic in time, you have to make a good tie between the well data and seismic cube. And then you use these seismic data and seismic attributes to build your input sheet, and you have the porosity, and then you start doing the machine learning algorithm to find the relationship between seismic attributes and porosity log, and then you have already the relationship. You can propagate it into the 3D directly. Great and informative. I'm so happy with this comments. Thank you very much. Can someone send the attendance sheet? Thank you for all of the practical example. It's my pleasure. Which IDE should be focus? Jupyter notebooks. Yani, don't get stuck in these things, because everything is working. In Jupyter notebooks is working, PyCharm is working, Sublime is working, VS Code is working, all the IDEs is working. Whatever makes you comfortable, go with it. Thank you for the presentation. Here is gentlemen and ladies. Here is ladies and gentlemen. Here is the attendance sheet. Please go ahead. The Gaussian is used in reservoir property modeling. Is machine learning works in the same way or in another way? In another way. We have already machine learning models based on Gaussian distribution and based on Gaussian models and based on which theorem, I will come to it, but we have this models already, machine learning models based on this series, but it works in different way. In Gaussian distribution, you basically do a random distribution for the data, but in machine learning, you are trying to link the data to each other, and this is a very important thing. So we have the Gaussian theorem, but in different ways. Thank you so much. Thank you, Yasmin. Thanks so much. It's my pleasure. Thank you so much. I think it's my pleasure always. Can I get your GitHub? Yes, I would like to share with you my GitHub. Much appreciated. It's my pleasure. Okay, before I give you my GitHub, I would like to thank you very much, and I'd like to thank the organizers and for their dedication. Actually, we have been planning to do this, I think it's a long time, and it's really a very important event. I enjoyed it very much, and I hope you enjoy it too, and I hope we already meet again for much any event or more events like this. For people who sorry, I just wanted to share with them my my GitHub. For people who wants to have my GitHub, it's here. And by the way, this is already the presentation. Today's presentation is already liquidated in this repo, and you can download it, of course. And I was going to send you to you, Aya and Ferial, the link to the presentation in order to distribute it with everyone here. I can't thank you enough for this, and the mic is yours, Aya.
Thank you very much, sir. Of course, you can send us anything they can need for this course to learn, and we will make sure to share it with all the participants via email. And we would like to thank you for being with us here today, for sharing your knowledge and experience with us, and for giving us some of your time. And we hope we can see you in our near events, and maybe if you come to Algeria, we would be pleased to welcome you in our events.
Thank you very much. It's my pleasure, actually. And Algeria, one of the countries in my bucket list I would to visit. And believe me, I will contact you when I will be there, inshallah. Thank you very much.
Inshallah. Thank you, sir. Thank you.
Thank you.